analytical geometry, which deals with plotting points and lines and circles, etc., in the Cartesian plane. First and foremost, we need to know how to identify and name points by an ordered pair, an x value, then a y value. Right, let's look at the formulae that we get given in this topic. So there are a total of 7 of them, and I'm going to talk us through each of them kind of as we go. The first one is to find the distance between 2 points. Now, I actually don't use any of these formulae. You're very welcome to, but I prefer to kind of visualize what is going on, and I think it's more powerful, and hopefully you'll see why, but let's just have a look. Basically, so what I would do if I was trying to find the distance between these 2 points, I would construct in a right-angled triangle, and I would now say, right, what has happened to my x value? Remember, this is your x value, going from here to here. It's gone from -3 to 6, so it's actually grown by 9. The y value has gone from 2 down to -10. It's changed by 12. It's actually a -12, but for the purposes of Pythagoras, we don't really need to worry about that. So the length of this line is just going to be, because of the right-angled triangle here, it's just going to be the square root of 9 squared plus 12 squared, right, which happens to come to 15 in this particular case. Right, if you prefer to use the formula that gets given to you, you're most welcome to do so. Right, sorry, went the wrong way. Let's now look at finding the midpoint of a line, and maybe this is where you'll see the way I prefer to do this. I would prefer to say, right, to find the midpoint of this line, what's happened to my x value as I've moved across? I've moved across by 9. Now, half of 9 is 4.5. So I either need to add 4.5 to -3, and I get to 1.5. Or if I subtract 4.5 from 6, I get to 1.5. With the y values, I've gone a total distance of 12. Half of 12 is 6. So if I come back up 6 from -10, I get to -4. And likewise, if I drop 6 from 2, I get to -4. So now the reason I think that's a more useful way of visualizing this is that if we were asked, for example, to find a point C on AB such that AC is twice as long as BC. So in other words, basically what we want a point in here, C, so that this length is twice as long as that length. What that's going to require is that we come 2/3 of the way along. Now remember, our total distance between -3 and 6 is 9. 2/3 of 9 is 6. So I must add on 6 to my x value. I've dropped down by 12. 2/3 of 12 is 8. So if I drop down 8 from 2, I get to -6. And now you'll see that the remaining distance is 4, which is the 1/3. So this method of kind of visualizing in terms of what proportion of the way one wants to go along the line for both the x's and the y's is probably more powerful than a formula, because it enables us to answer questions like this one. But again, if you prefer to use a formula, you're very welcome to. Finding the gradient of a line. So what I like to do here, again, I like to say, well, what's happened? My sort of thing in my head for gradient of a line is rise over run. Remembering that a negative rise is a fall, and a positive rise is a rise. So this is a negative gradient, and this is a positive gradient. Because we're in a country where we read from left to right, we're always moving from left to right. So what's happened here, this line's got a negative gradient. It's dropped down by 12, so the rise is going to be negative, and it's run across by 9. So the gradient, rather, of this line is negative 12 over 9, or negative 4 over 3. Again, you can use the formula. If you do use the formula, make sure that you don't swap these points around. In other words, you take the y value of this point minus the y value of the other point. Then you must start with the same point and take its x value. Don't go y value minus y value over x value minus x value. You'll then get the wrong sign for your gradient. As soon as you look at a line, you'll know negative gradient or positive gradient. If it's sloping downhill, it has a negative gradient. If it's sloping uphill, it has a positive gradient. Right. Finding the equation of a line. Now, there's quite a lot that goes on here, And I'm going to, in fact, show you 4 different methods of doing this. Okay, so we get given these 2 formulae on the data sheet. Both of them involve m, the gradient. So let's just have a look. This line's clearly got a negative gradient. It's dropped down from 5 to -3, -8, and it's run across from -1 to 3. It's actually gone across 4. So it's got a gradient of 2, right? At this point, what we do, we can use either of these formulae, and I'm going to show you. We can write down y equals mx plus c. So I'm going to write down y equals 2x, sorry, it's -2, -2x plus c. Right, and now I'm going to substitute in a point. I can use either point. So 5 equals -2 times -1 plus c. So in fact, I get that c equals 3. And I then write my final answer down, y equals -2x plus 3. I personally prefer to use this one. You'll see that it's kind of one less step of working, because I go y minus a y value is the gradient x minus an x value. In fact, I don't need to write this step down, but I did write it down here. And as I'm comparing the 2 methods, let's do the same for both. So y minus 5 is -2 into x minus -1, so it's x plus 1. So this becomes y equals -2x. I've got a -2 here, but I'm going to add a 5, and I get a -2x plus 3. Notice that I've used one line less working. The third method, right, so it's kind of method 1, using that formula. Method 2, using that formula. Both of those methods require us explicitly at finding the gradient. The other thing that we can do is we can just substitute both points into y equals mx plus c. So 5 equals -1 for x times m plus c, and -3 equals 3m plus c. Now I want to solve these 2 equations simultaneously. Subtracting them, right, if I subtract them, the c's will disappear. I get -4m, because that's -1m minus 3. I get -4m. 5 minus -3, I get 8. So I get m equals -2. And then I sub that value for m into either equation, and I get my c value of 3. And I get my final answer of y equals -2x plus 3. Sorry, -2x plus 3. So that's method 3. And lastly, as you know, our calculator can do by line of best fit a kind of line of best fit through those 2 points. So what I could do is I could just go into mode, stat, and I'm going to choose this option 2, same one that we use for line of best fit in the stats module, which we'll talk about later. And I need a line that's going to go through -1, so -1 on x, and 5 and 3, -3. So I just put my 2 points in, press all clear, go shift stat 5, and I can get my a value. Remember, it's a plus bx. So the a value, in fact, will be 3, and shift stat 5, 2 for the b value, and I get -2. Just for fun, you might want to look at the correlation coefficient of that, and it shouldn't surprise you that, in fact, you will get 1, because it is it's a perfect correlation. That's the line of best fit, obviously, going through those 2 points. And so method 4, if I can just get my pen back, method 4 is just to do a line of best fit on the calculator. One doesn't need to show any working at all. Okay, so the next formula that we get given involves this, m equals tan theta. And what it's saying is that the gradient of a line is the same as the tan of the angle of inclination. I'm just going to show you a little simulation of this particular one. Right, so what we've got, an angle of inclination is always measured from sort of 3 o'clock on the clock face, going anti-clockwise around. So there's the angle of inclination. It's 56.2. And if we find the tan of 56.2, we get the same answer as we have for the gradient of this line. Now, if I go and drag this, you'll see that that remains true all the while. At 90 degrees, both the gradient and the tan of the angle would be undefined, and it might be difficult to get them to 90. There we go. I did see a question mark there. all right? There's no gradient for that line because you're dividing by 0. But watch what happens when we now go negative. It's still true that the tan of the angle of inclination is equal to the gradient. Notice, though, that the angle is now obtuse, and the line has got a negative gradient. The tan of an angle that's obtuse is negative. So it all kind of takes care of itself. Let's see how this plays out in actually doing an example or two. So here's an example, and what I'm going to do is I'm going to find the angle of inclination of both of these lines, all right? So I'm just going to start off by getting a sort of horizontal line tool. So what I can do is I can put a line in anywhere here, a horizontal line. So when I'm working out the angle of inclination of this line, it'll be that angle over there, and I'm going to call that theta. But when I'm working out the angle of inclination of this line, remember we always start at 3 and we go anti-clockwise, it'll be this angle there, which I'm going to call alpha. Now let's do the uphill line first. It's got a positive gradient. It's rising 3. It's got a positive gradient, and it's running across 5. So literally the tan of theta will be 3 over 5, and so theta will be the undue tan of 3 over 5. Let's look at this one. What happens here, the gradient is negative 5 over 2. I think I'm right in saying it's dropped down by 5, and it's run across by 2. Right, so let's now go to our calculator and see what happens here. So we seem to have lost the calculator. There it is. Okay, so the first one's very straightforward. Shift tan of 3/5, and I get about 31 degrees. The next one, slow learner, sorry, lost the calculator again. The next one, I'm going to undo tan. Now, the way I would do it personally is I wouldn't put the negative into the calculator. That would give me a key angle, right? I know that so let's just go undo tan of 5 over 2, and this will become clearer once you've watched the trig video, which doesn't exist yet, all right? 68 degrees. Now, basically what I've got, I want an angle that's in the second quadrant by 68 degrees off the horizontal axis. So this angle over here, where my mouse cursor is 68. So this one over here will be 112, right? So just to close that out, the angle of inclination of this line, this angle theta, is going to be 31 degrees, and this one's going to be 112 degrees, right? So the answer that your calculator gives you, if you put the negative in, it actually gives you this angle over here, because it gives you a negative angle going around there, and it'll give you negative 68 degrees, all right? I didn't put the negative in. I got a positive 68, and I subtracted it from 180. All right, so that's angle of inclination, really important concept. Okay, let's look at an example now. We asked to find this angle over here. So there's a couple of different bits of maths that we could use here. One, we could find out the distances of all these sides, and we could use our cosine rule from trigonometry to work out that angle. That's actually a much more work than using the angle of inclination idea. So what I'm going to do is I'm going to construct in an angle over here. Sorry, not an angle, a horizontal line. Okay, and what we've now got, we can easily find this angle over here, which I'm going to call alpha, right? Because alpha is just going to be undue tan of the gradient of this blue line. The blue line's risen by 4 in the time that it's run across 2, right? We get about 63 degrees here. It's very easy to find this angle of inclination as well, right? And this one is just I'm going to call this one beta, right? Beta is going to be 180 degrees minus the undue tan. And I'm not going to put the negative value of this gradient in it. This line has got a gradient that's going down 3, and it's running across 4 from negative 1 to 3. So this here will give me the size of beta. right? And I'll quickly get that for us. So we get 143 degrees. Now, this angle is exterior to this triangle. So we know that, in fact, beta will be the same as alpha plus theta. The exterior angle of a triangle is equal to the opposite interior angle. So obviously theta will be beta minus alpha. So 143 minus 63, about 80 degrees. Right, and that's much simpler than working out all the lengths, etc. Okay, let's take a look at circles, a really, really important concept. So we get given this formula over here. It's important to understand where this formula comes from. It's just the distance formula, because the way a circle is defined is a set of points that are always r units away from this point AB, the circle, the center, 0, AB. So if we express that mathematically using our distance formula, basically we want x take away a, all squared, plus y take away b, all squared. If we add those together, we would get r squared, all right? And that's just exactly what the formula is. Okay, so important to understand where it comes from. So let's just take a look at a sort of a simulation of this, which hopefully will be helpful to you. So what we've got here is we've got a circle, and I can change r, the radius, and make the circle bigger, right? If I change a and b, we'll see the format of this circle. So this is a circle here with a center of 12, 5, and a radius of 5. Again, I can make the radius bigger or smaller. Let's just move this across a little bit. This one over here, a center of negative 11, 0, and a radius of 7. And it's now got a center of negative 11, negative 4, and a radius of 7. Right, and then lastly, negative 11, 6, and a radius of 5. Okay, let's have a look at an important concept now. One of the things that we really need to be able to do, and we need to be good at it, is we need to be able to write a circle into standard form, back into that form. So let's take a look at how that's going to look. Right, I want it basically as some x's plus something squared or minus something squared. I want it into this form over here. Right, now remember, when I square out, whatever I put over here will multiply with the x and then double. So I need to take that and halve it. Right, and likewise, I need to take the minus 8 and halve it. If I was to multiply this thing out right now as it stands, I would get, on the left-hand side, I'd get exactly what I'd had, but I'd get a plus 4 from squaring the 2, and I'd get a plus 16 from squaring the 4. Effectively, I've added in 20. In order to keep the balance, I've got to add in a 20 over here. And obviously that comes to 100. So this particular circle actually has a center of negative 2, 4, and a radius of 10. And it's really important that we're able to do that. Now, this one over here, just be aware, this one is slightly unusual in that we've got our y doesn't have an offset. So in other words, it's just going to be like that. By writing it like this, if I multiply it out, I've added in 9 on the left. So I've got to add in 9 on the right. I get 16 plus 9, which is 25. So this circle has actually got a center of 3, 0, and a radius of 5. Very, very important skill that you can do that. Right, now I'm just going to give you some ideas of how questions manifest themselves and how important they are. Right, so the first question that one might sort of come up with, we're given these two circles and it says that this thing's not necessarily drawn properly. Do they cut? Do they touch? Do they intersect? Well, the first skill would be to find the centers and the radii of both of them. This one's got a center of 3, 2, and you might want to pause the video and confirm that. And this one's got a center of 8, 2. This one here has got a radius of 5, sorry, square root 5. And this one here has got a radius of the square root of 9, which is 3. Right. Now, if I work out the distance between these 2 points, the straight line distance between these 2 points, I'm just going to bring up my kind of straight line tool. If I work out this distance and it exceeds the sum of the radii, the sum of 3 and plus 3 plus root 5, that sum, then obviously the circles don't they don't touch one another at all right? If it's exactly the same, then the circles will touch. They will sort of be tangential to one another. And if it's less, right, this blue dotted line is less than the sum of 3 and root 5, then obviously we have an intersection, which is what we've got, and they cut one another in this situation here. I'm not actually going to solve the question. This one is actually drawn to scale, so these ones do actually cut. Another really important skill, right, is to find the equation of a tangent. Now, there's an important piece of Euclidean geometry that comes in here, and that is that a tangent and its radius are always perpendicular to one another. So what we've got here, we've got a right angle in here. And what that enables us to find is the gradient of the radius. So it's dropped down by 1. It's clearly a negative gradient. And it's run across by 2. So this line over here has got a gradient of negative a half. Because of the perpendicular, the radius and the tangent being perpendicular, this line, remember to find a perpendicular gradient, we turn it over and change the sign. So in fact, this tangent has got a gradient of 2. And now I'm going to use my y minus a y value is the gradient x minus the x value. And so I get y equals 2x. I get minus 20 here, plus 1. Sorry, minus 20 plus 1 is minus 19. That's the equation of the green tangent. An interesting question is to find the length of the black tangent. Now, the reason I say it's an interesting question is because we don't know this point. If we knew this point, it would be easy. But what we do know, once again, we know that there's a right angle in there, and we can easily work out this length. So this length here, which I'm going to call L, I can easily work out using the distance formula. This length over here is the radius, all right? And that can easily be found. We know it already. It's 3. So AE, the length of the black tangent, squared plus 3 squared equals L squared. And remember, I can work out L. So I know this piece, and I can work out the length of this tangent. You might say, aren't there 2 tangents? They are, but in fact, the other one that comes through over here somewhere is actually equal in length anyway because of the Euclidean geometry result. Right, so that's an important concept. One can work out the length of a tangent without actually knowing its point of contact. The very last thing I want to look at is just finding the missing corner of a parallelogram. Right, so we asked to find D if ABCD is a parallelogram. And I'm going to show you how easy this is to do. One might be tempted to say, well, let's have a point here, and that point would obviously be the intersection of these 2 missing sides of the parallelogram. We could work out the equations of those 2 sides and solve them simultaneously. But in fact, if I just picture what's happening as I move from B to A, because the opposite side of a parallelogram is not only equal in length but has the same gradient, what happens is from B to A, exactly the same thing needs to happen as I move from C to D. So if we look, as I move from B to A, think of it as a vector for those of you that do science, my x value decreases by 7. So as I move from C to D, my x value must decrease by 7. My y value decreases by 2, so my y value must decrease by 2. And that's the value of point D. You might say, couldn't we have used this side as the kind of vector? And indeed we could have, because if we have a look and we move that across, as I move from B down to C, my y value must drop 5. And if we have a look, my y value dropping 5 from 1 to minus 4 is correct. And my x value must reduce by 1. And notice as I move from B to C, my x value is reduced by 1. And my x value here has reduced by 1. So I get the same point. Right, so you can literally just write the answer down. Right, and that brings us to the end of our video on analytical geometry. Obviously, it goes without saying that the main thing is to practice examples.
As always, if you found this video useful, please subscribe, like, and share. Thanks and have a great day.